Hey class, today we're going to finish out chapter 8, section 4, and we're going to learn about a couple other ways that things can bond. So, there are two types of forces that play a role in the behavior of molecules. We've been focusing on intramolecular forces. So, these are going to be things that occur within a molecule. These are going to be things that hold atoms together. So we've talked about covalent bonding. Last chapter, we talked about ionic and metallic bonding, but this section is going to focus on something called intermolecular forces. And these are going to be things that occur between different molecules. So for example, how does one O2 react with another O2? Or for example, how does one H2O react with another H2O? So again, one's within a molecule and the other one's between molecules. So our key question we're going to ask is, how do the strengths of intermolecular attractions compare to intramolecular attractions? Remember, intramolecular attractions are ionic and covalent or metallic. What we're going to notice is that intermolecular attractions are weaker than both ionic and covalent. But the reason we talk about them is because they are responsible for a lot of physical properties that we see within molecular compounds, such as what state of matter does it take, the boiling point, and melting point. So there are three types of intermolecular forces that we're going to talk about, and we're going to talk about them from weakest to strongest. The first one is van der Waals, which we call London dispersion forces. Next, we'll talk about dipole-dipole interactions. And then last but not least, hydrogen bonding. So first, let's look at van der Waals. This is also known as London dispersion forces. This is the weakest of all intermolecular attractions. One thing to know is that van der Waals occurs in all molecules. Does not matter if it's a polar molecule or a non-polar molecule. Every single molecule has van der Waals attractions happening. And the reason for this is because every single molecule is going to have electrons moving. And whenever there's electrons moving, this is when we're going to see this type of force having an effect. So what do I mean by motion of electrons or electrons moving? When the moving electrons do this, they might happen to be momentarily more on one side of the molecule than on the other. And so when these molecules are moving around within their different orbitals, they are going to give off an electric force that's going to influence any neighboring molecule's electrons around. Now, this influence is only momentarily, so it's kind of like if you have two balloons with water and you swish the water back and forth, it's going to momentarily be on one side and then it's going to shift and momentarily move around the other side because these electrons are always in motion. Now, the strength of a dispersion force is generally going to increase as the number of electrons increase because you have more electron movement. And like we said, these intermolecular forces affect physical properties. So for example, chlorine and fluorine have relatively few electrons, and you're going to note that these are going to form gases, and that's just because their dispersion forces tend to be weaker. Bromine, which has actually more electrons than fluorine and chlorine, tend to be a liquid, again, because now that I have more electrons, I have a little bit stronger dispersion forces. And then last but not least, iodine. This has even a larger number of electrons, and we're going to see that it tends to form a solid at room temperature because it has even stronger dispersion forces. The next type is dipole-dipole. Dipole interactions are going to occur between polar molecules. And so dipole interactions are not going to be found in nonpolar. So not found in nonpolar molecules. So example of a nonpolar molecule would be things like O2 or F2. those are not going to see dipole interactions or dipole-dipole interactions. We're only going to see that if we have that polar bond, because the electrical attraction between the oppositely charged regions have a bigger effect. These are not momentarily attractions or partial attractions. These are going to be fully attracted. Okay. So what do I mean by that? Let's say we had a polar molecule. So here, let's just say I had hydrogen bonded to fluorine. Okay, again, we have hydrogen bonded to fluorine. So HF. These molecules are going to be attracted to other molecules. And what they do is the slight negative end of one molecule is going to be attracted to the slightly positive end of a different molecule. Keyword, different. And that ends up forming a slight interaction or a slight bond. You can kind of say that this is similar to an ionic bond, but much weaker. And it's a little bit different than an ionic bond because it's happening between molecules and not within the molecule. Now, dipole interactions in water, what's kind of cool about it is that there are going to be polar bonds within water molecules. We see oxygen and hydrogen bond tends to be highly polar. Those electrons are going to be pulled closer to oxygen, giving it a slight negative charge, so slight negative. And then hydrogen is actually going to be slightly positive. And again, we talked about this in the last lesson. This has to do with electronegativity. Now, this is going to lead into hydrogen bonds. Now, hydrogen bonds are going to have dipole bonds because they are polar. However, they are actually a special type of dipole bonds. So hydrogen bonds are a special type of dipole bonds. What do I mean by special type? We are still going to have a positive region affect a negative region. So for example, if I say that this is oxygen bonded to 2 hydrogen, again, this is oxygen bonded to 2 hydrogen, we're going to notice here we have oxygen bonded to 2 hydrogen. We're going to see that the hydrogen, which is positive, is going to be attracted to the negative side of a different molecule. However, because this is actually going to form a really, really strong attraction, we actually call this a hydrogen bond. Like we said, this is a stronger type of dipole bond. Now, hydrogen bonds will not just occur with any molecule. Hydrogen bonds are actually defined as the attractive forces in which hydrogen has to be bonded to a very electronegative atom. So that means, like I said, not every bond with hydrogen is going to be a hydrogen bond. It typically only occurs with those highly electronegative elements such as oxygen, nitrogen, or fluorine. My professor always told me, remember FON or FUN, I don't know. That always helped me. And so when we use the example of water, this should make sense because we have hydrogen bonding with oxygen, which is super electronegative. Now, one thing to know about hydrogen bonds is that they are the strongest of the intermolecular forces. However, they are only about 5% the strength of a covalent bond. Because remember, covalent bonds are intramolecular. So again, while they are the strongest of the inter, they are still weaker than intramolecular bonds. The reason we care about hydrogen bonds is it's very important, especially with water, and it helps determine a lot of properties we see with water. For example, water has really, really, really high specific heat, which means it can actually take in a lot of heat without warming up a lot. Water adheres to things and is very cohesive. So those are a couple attributes we see that are important for water. So why are properties of covalent compounds so diverse? It comes down to there are different intermolecular attractions happening. So let's look at this. If I have something like F2, F2 is a nonpolar molecule, And so you're going to see that this one only has London dispersion forces occurring. Whereas if you see something, let's say, like HCl, this is actually a polar compound. And so this is going to still have London dispersion because every molecule is going to have London dispersion. However, this is also, since it's polar, going to have dipole bonds as well. Now, it's not going to have hydrogen bonding because it's not bonded to a super electronegative atom. It's not bonded to nitrogen, oxygen, or fluorine. Then we have something like HF. Here, HF, this is a polar molecule. Since it is a molecule, every single molecule is going to have London dispersion forces. Again, always. This is polar, so it's automatically going to have dipole bonds. And then we're going to see, well, hydrogen's bonded to an extremely electronegative atom, again, to fluorine, oxygen, or nitrogen. So we're going to actually also see that this forms a hydrogen bond as well. So we have to kind of see what bonds are happening inside these compounds. Last but not least, there are a few compounds that form solids, and they consist of molecules that do not melt at very high temperatures. And these covalent compounds we sometimes call network solids. These are very, very, very stable, and they are stable because all of the atoms are covalently bonded to each other in such a way that it creates this big, huge, very strong network. And it takes a lot of energy in order to break every single one of these bonds that are holding it together. A good example of this is diamond. Diamond is only made up of carbon. Each carbon is covalently bonded to 4 other carbons, and they are interconnected and form this network where it takes a lot of energy to break each of these individual bonds. And so carbon is very, very, very strong, and it does not melt at very high temperatures. It just ends up vaporizing. And that's it for today's lesson. Let me know if you have any questions, and I hope you guys have a great day.